Okay, so let's start the last lecture by Remi on probabilistic construction. And please, Remi, the screen is for you.
Thanks. So yes, I will finish the story about the Liouville model by explaining a bit the bootstrap. So perhaps this is I guess the part you are most familiar with. Now, the game will just need to combine the tools I've explained to proceed to the series of steps that are more or less the same for any approach to CFT. So basically, in our context, we will compute the bootstrap. We will decompose each Riemann surface into pairs of points. But the points, you have 3 options because the marked points count as an end of a point. So you have 3 options, these 3 ones here. Okay. Of course, there is also the Riemann sphere with 3 points, but it's not what I call the building block. You cannot get it from sketching a surface. Okay? You have always a cut. If you cut the surface. Okay, so you have these 3 points. So the points here, the holes are not, well, they are analytic holes, not straight holes necessarily. Okay. So you have 2 examples here. So you can have a surface of genus 2. You have these 3 cuts. It gives you 2 points here, left, right, with 3 holes. That's one example, right? And you have the sphere with 4 points that you can cut with a circle in the middle at the equator, and you get 2 points, meaning for each point, 1 hole and 2 marked points, right?
Can I ask a question there?
Yes.
Why, so philosophically, why do you distinguish the situation of having a marked point and having a hole? Because in last lecture you had you could generate a state in your Hilbert space by a disk with a point in the middle.
Yeah, it's not. I don't make a distinction. It's more or less the same because if I have a marked point, what I could do is just I cut a hole and then insert the corresponding state in between.
Right.
So then I can choose. I can make a hole here, choose a system of coordinates, and replug any primary state.
Right. I think my question is why not just work with holes?
Because that's if I give you a closed surfaces with only marked points, this is one further step to explain that I will decompose into points. So it's just a matter of point of view, but doesn't matter so much. Okay, so you have these 2 options. So the procedure is you decompose your surface into pair of points, and you get some building blocks like this. These guys, they will be glued together, and at each gluing pair, you will insert the spectral decomposition. And so what you will end up with is just, if you see this guy as operators, you will just have to compute the matrix elements of these guys when evaluated at the guys in the spectral decomposition. Yes.
Maybe I can just make a small comment about this question. For the boundary, we usually consider them as elements in the Hilbert space. While if you cut near an alpha, the problem is the amplitude is not in the Hilbert space, it's in a bigger space.
Okay.
Weighted. So it's kind of equivalent, but there are technicalities. The alpha here, they are not on the spectrum somehow.
Yes, they are not in the spectrum, but still when you glue, you get the same regularity.
Yeah, but
well,
I think this is the reason why we distinguish, at least that's why I understand it.
So can I have a follow-up question there? So you're saying if I've got these 2 marked points, then I land in the Hilbert space, but with just 1, I don't?
But when there is only 1 marked point?
I didn't understand the comment.
It's just that the states, the alpha here, they are typically on the real line.
Okay.
So the C alpha is not in the Hilbert space.
Okay. C alpha is not in
the alphas, when you start from probabilistic expression, the alpha are real. Okay, of course, you can analytically continue them. You can show that it's analytic in the alphas. But from scratch, when you have a probabilistic expression, the alphas are real. The spectral line is a Q plus IR. So it's the imaginary line shifted by Q. So it's if you draw your plane for the alpha, you see here or not? This is the if you have Q here, this is the spectral line. So this will be the states that you plug in the holes, and the alphas, if you are from the beginning on the surface, they are on this line. But I told you there is an analytic continuation between the two. So basically, if you compute them for any red or blue line, then you can continue, provided that they satisfy some global constraints. But reasonably, you can say that you can continue the correlation. Okay, so the next step is to compute the matrix element of this band amplitude. Okay? And I will discuss only the general setup where you have 3 holes. Okay, and for me, so you cannot always uniformize this band with 3 holes. So it amounts to choosing 3. So you can see the band with as the Riemann sphere with 3 analytic disks removed, and these analytic disks they are given by holomorphic maps in the disk mapped onto the Riemann sphere. So it gives you the 3 disks. So that clear or not? Okay, the parameterization of the boundary are just the psi j of the circle. Well, the metric you have to take it in coordinates admissible. It's regular enough in coordinates. It means that locally near the cut, the metric is the metric of the cylinder. And so this point amplitude, so it's an element in H3 if you take 3 in parametrization. Well, actually, it's an operator, but I will consider the amplitude as the integral kernel of this operator. Okay, so the game now, what I want to do is to explain a little bit what you will. Okay, how you get the one identities here. So when you have an amplitude, you want to compute it on the spectral elements that are indexed with Young diagrams. So this means these Young diagrams, I will write it differently, means that you have Virasoro generators acting on the primary state. Okay, and the new here is a Young diagram. This means that there are several Virasoro generators indexed by the Young diagram. And so the game with this amplitude, the satisfy identities that will allow you to get some relation with the LNs in the holes. Okay, so how you will do this? We have seen that the LNs, they come from playing with this semi-group of annuli. Okay. And this is the infinitesimal generator of the semi-group of annuli. So basically, you can get this guy if you glue some moving annuli at the boundary of your surface, differentiate, and you will get some relation. Okay. So that's what I want to explain. So to do this, you can perturb the boundary parametrization with maps that are holomorphic near the circle. So if you have your point, you can have your point like this. Okay, so the point is the interior. Okay, I shouldn't. Yes, not. And so if you apply a flow FGT in the whole number J, you will deform the boundary, not necessarily shrinking, but you will deform the boundary. And the game is that the amplitude is now given by the boundary, the green boundaries, and you want to to find what happens to this new amplitude. So there are some abuse of notations here. FJT is not defined on the disk. It just means here the domain is given by the new boundaries that you have perturbed. Okay? It's not true that I can consider the image of the disk by FJT. It's an abuse of notation. Okay, so once you have this, so because of this FJ being not holomorphic in the disk, when you compose on the right by this FJ, it's not a model of your annuli, right? Because the points, they are parameterized by holomorphic maps in the disk. Yes.
Just to clarify, so your FJ, it's a flow. It
Yes.
is on the
It's a flow
disk, but it's in some annular neighborhood of the circle.
Yes.
But it's okay. Is it in what pointing as before? Or?
Not necessarily. It's a holomorphic function, but near the circle. So the vector, it's generated by a vector field, and the field is not necessarily pointing inward. So the boundary may be.
How do you apply psi j if you go out of the disk?
Because psi j is a analytic in the neighborhood of the boundary. Okay? So you have some room to play with the FJ.
You mean you extend them smoothly because you apply them to the disk here. They're just analytic near the circle, but you extend them smoothly.
Yes, what I mean is that this is an abuse of notation to say that I remove the hole created by this new boundaries. Okay. Okay, so you can always uniformize with a map psi to put your model under a model form, meaning that you have three holes, the new holes parameterized by holomorphic maps. And for the metric, you just push the metric with this conformal map. Okay, and the thing is that if you view, you can always view the new curve. So, for instance, if I make a zoom around the here, you have the old boundary, the new one. I will put it in blue. You have the new one. But as I said, you are analytic. The coordinates, you can always cut a bigger hole before. And so you are just seeing what happens when you deform this boundary here to this new one. Okay? So even if it means you get a bit larger, you can always say you have an annulus amplitude. Okay? And so you are moving this annulus amplitude, and the differential of this guy, basically, they are given by this ln. Okay? So there is a theorem. I don't explain all the set, but it's really based on the fact that you can localize these guys as the action of the annulus amplitude near the boundaries. Okay, and you have this formula that tells you that the new amplitude, they are differentiable, and the derivative is given by this ln applied to the boundary, to the corresponding boundaries. The VG here are just the vector field that generate your flow of maps. Okay. So now if you start from okay, so that was a generic situation for different vector fields at different holes, but it may be the case that all the vector fields generating the flow near each boundary come all from a global vector field defined in the neighborhood of the boundaries of the plants. So it means that if you have your point here, the vector v, you may have a vector v that is defined on the neighborhood of this point. Okay, so that the flow of conformal maps is globally defined on the surface for small t. And you just see the action of this guy near each boundary, but they are related by the fact that they come from the same vector field. Okay, so if you do so, so the new point is then, because of this, you have this flow of map. The new point is conformally equivalent to the old one, and so that you can play with the anomaly coming from the metric to have this anomaly term. So it just comes from the veil anomaly. The amplitude of PT is related to the old one HE. And if you differentiate, combining with the formula I gave you before, you just have to further plug this differentiation of this factor in front. And if you make some computation, you end up with this formula that is called the Ward identity. So the sum of the three, the amplitude applied to the sum of, the sum of these terms, where you have composed by the Virasoro generators, up to this Schwarzian term here, sum to 0. And you have the same formula for the other copy of the Virasoro region.
The J in the LVJ, J means you act on the J's component, right?
Yes. Yeah, there are 3 holes here. J, well, this index, it can just mean that you plug in the J's component.
How do you separate the L from the tilde in your?
Sorry?
How do you end up with? How do you manage to separate the equation for the L from the L tilde? That was only in the same one before, and now you have 2.
Well, one way is this formula here. You can play with the Vn. There are complex numbers. You can play with the Vn to separate the guys. Yeah, actually, you can also get this formula for any age. And this age, playing with the coefficient, you can get the formula for the V, the ln's and the ln's still.
But the amplitude, they always have both. You can't, at the level of amplitude, you can't split.
At the level of
the annular, sorry.
Well, you can also define the action of the age, but on the holomorphic part of your Hilbert space, and then you get this formula. So
Linear combination.
it's just a linear
Complex linear combination of all these identities.
Okay, so yes, so you have this formula, and now you want to compute these guys here. So I will be a bit fast with this factorization. So this is a holomorphic factorization. So here you plug general states. They may be descendants, and there is a statement that says that the matrix elements here they factorize. So what do you have inside? So you have a metric dependent constant that is not that much important. Well, it is, but the main part is right. So you have those coefficients. Those coefficients are just a collection of the Q plus I pi G, PG, that you plug in those formula. Okay, you have 3 of these guys. You have 3 positions in the dose that fits. And then you have coefficients, W. And the factorization that you get is really the W's. They depend on the news, the Young diagrams, and the complex structure of the P. Okay, you get an expression times this, it's a complex conjugate. But this time applied to the P tilde, the new tilde. Okay, so the general strategy is the same for I think in your approach. The thing is that you have descendants in all the holes. Then with Ward, you can move the guys from one hole to the other. Then I should, well, then when you have descendants only in 2 holes, you can play with Ward again to push everybody in the last hole. And then when you have everybody, all the LNs in the last hole, you realize that Ward tells you that having descendants in one hole amounts to applying differential operators to the structure constants. Okay, it's not quite a simple story, but still, I think it's the same for everybody. And there are subtleties that I want to skip. So basically, in the end, you have a collection of differential operators that you should apply to this guy. Just to give you how you compute this guy. So if you compute this guy here, again, the primaries that are on the spectrum line, you analytically continue them in the parameter alpha to the probabilistic region. And so that in the end you compute these guys with the alpha that are real and the less than q. Okay, but in that case, you know that there are amplitude of the disk with a marked point. So by Segal, the Segal functor tells you that the amplitude of the point applied to this guy is just amounts to computing the gluing of 3 disks to the ends of your point. Okay, and by Segal it tells you that this gives you a sphere with 3 marked points, and so this is the dose formula up to this completely explicit expression for the variable. And then you have differential operators that are rather nice. You apply them to these guys on the right here, this one, and you realize that you get your W's. Okay. This is how you compute the W's. Okay, so this is a long story short. And then I just explain how we start knowing the holomorphic factorization, how you compute the partition function. For instance, I give you just 2 examples for the conformal bootstrap rather than general statement. So you may want to compute the partition function of this surface of genus 2. So there are several ways. Well, one thing, if you are not familiar with probability, one thing that is super important here, you want to compute the partition function of this surface. From scratch, there is no cut. Okay? So the cuts are arbitrary, and they may be not isotopic. Well, the correlation function, they don't depend on the choice of the cuts. And why? Because you have a probabilistic expression for it. So all the problems that you may have, crossing symmetry and so on, in probability you don't have that. Because from scratch, you know that everything is consistent. Okay. That's one thing that's important here. So I choose a system of catching curves. It gives me 2 points. Yeah, right. But and by Sega, I know that the partial function amounts to gluing these 2 points together. So, and if I insert the green arrows, if I insert the spectral decomposition at each gluing, okay, I end up with this expression here. Here I sum over all the possible Young diagrams. Okay, here I have all the Shapovalov matrix coming from the spectral decomposition resolution, and in between I have this matrix element of point amplitude. And so by the holomorphic factorization, I know that these guys are those coefficients up to some W factor coming from each point. Okay, and if you combine everything, you end up with this formula that this partial function is the integral over the real line to the power 3, because there are 3 cuts of the dose coefficients associated to the cuts times square modulus of something, and this something is the conformal blocks that you form, and you get this expression here. Okay. So what I did, I just plugged the holomorphic factorization inside, and you end up with this expression.
Metric dependence is where here?
The what?
The dependence on the metric.
The dependence on the metric should be here, but I forgot. Yes, you're right that there is dependence. Yes.
So does this construction tell you that this sum is convergent, or you need this as an input?
Yeah. So yeah, sure. The big question is to know whether these blocks are converging, but so my teacher when I was young, he was always telling me there is no nice proof without the Cauchy-Schwarz. So here this is just Cauchy-Schwarz, because when you compute the partition function, you have 2 amplitudes here. It's a scalar product, and by Cauchy-Schwarz, it's always less than what you have. You can apply Cauchy-Schwarz, this scalar product on top. This one. Sure. Okay. Okay, and so in the scalar product, if you apply Cauchy-Schwarz, you will get this one paired with itself. It's a new surface of genus 2, and this one as well, right? Okay, so it can always give you and the blocks for these 2 guys is just well, well, the absolute value of the blocks are controlled by this identity in some way. Okay, so by Cauchy-Schwarz, you can show that the convergence of this guy amounts to applying Cauchy-Schwarz. So yes, the outcome is that it's converging. There is one thing here, is that, well, it tells you actually that this integral is finite. Okay? But here you have a modulus squared. Okay. So it tells you that this guy converges almost surely in P. Okay. So you can ask whether you can extend this convergence from almost surely in P and to convergence in P. And this is what Jean did with collaborating. Okay. But yes, again, oh, so the nice. Nice part of the question is that, again, the convergence of the block is reduced to a probabilistic argument because we have the probabilistic formulation. That part, again, is not that hard to convergence of the blocks. Okay. So the consistency and the convergence of the block is almost for free in this approach. The constraint is that you have from scratch to find the probabilistic formulation, which is not always straightforward. Depending on the model, it might be super complicated.
And the Plancherel formula is also difficult.
Yeah, but from scratch, yes, there are many technical steps, but from scratch, what is even less guaranteed is that there is a probabilistic formulation. Okay, so there is a general statement for all surfaces. So the outcome is that you can play. So here, forget the Q here. You have a general expression for all correlation function with all possible mark points on any surfaces, but I don't want, it's a lot of notation. It's just an informal statement that you can implement this construction for any Riemann surface. Okay. So now I'm not sure of the time, but I will say a few words about eventually two different topics, and maybe only one. How you extend this to the case of Riemann surface with boundary. So this is a ongoing project with Baojun who here and Colin. And okay, so the question is, there will be several colors in my talk, and they matter. So now you want to compute the partition function of the Liouville theory on Riemann surfaces, but that are open. They are completely different from the surfaces with open with boundaries that I was talking about a few minutes ago, because from scratch here, this green color means that you have a potential on the boundary, that the fields you are integrated over here fluctuates on the boundaries, whereas for the amplitude, the field was constrained to being equal to something on the boundary before. Okay, so it's different. So you have the field may fluctuate on the boundaries here. You have a potential on the boundary, and the question is whether you can compute the partition function of this surfaces in R points. And the Liouville model in this case is given by this action, this path integral. And the action here is the old Liouville action, but you have a further term on the boundaries. So here you have the geodesic curvature along the boundary, say this one. You may have marked points on the boundary. Okay, and potential here on the boundary. Okay, so by the way, I just saw Baptiste, and yesterday someone asked about VOA for Liouville. You should ask to this guy. Okay, so you can define. So I won't tell you in details how you construct the probabilistic path integral, but this is same flavor as before. And you want to compute this exponential, this vertex operator, the correlation function of these guys, where here, as before, the V alphas are exponential of the field at some given point xi. questions at this step? Or there is also one subtle sheet that here in the mu-v, the coefficient here is not completely constant. Actually, it's a constant on each part of the green curve. And if you have something between 2 points, this is one part. So you may have one mu here and one different mu on the other part of the curve. Okay, so in that setup, you can again construct amplitude. But then the color, so you have a bigger class of surfaces with boundaries. You have to cut your surfaces. As before, there will be something related to the cuttings of the surface, but now you have two types of cuts. Okay. The big difference is that in the case of closed Riemann surfaces, you had to choose cuts, but there were loops on your surface. Okay. Now, what you can do is you are allowed to have a further cut. So if you start from here, you may have you have mark points. You may cut like this if you want. So you have always the bulk cuts, but you can perform some boundary to boundary cuts, meaning that you can start from the boundary, make a cut, and come back to the boundary. Okay. So these types of cuts are allowed, and they are different, these boundary to boundary cuts, from the bulk cuts. That's why you have this kind of weird part here. So the cuts are blue when they are in, because there are again two parameterizations. They are blue when they are in, but you have typically here this is it comes from a bulk cut, and here that part here comes from a boundary to boundary cut, and this part in green is the original green boundary where the field may fluctuate. So here the field on the green part may fluctuate, but here it's constrained. It's constrained to take on some prescribed boundary value. Okay, so it's similar as before, but you have several possible groupings. Okay, so you can extend the construction of the Segal functor. This means that you can glue the blue curves to the red one, provided that they are both boundary to boundary or bulk to bulk. So you can glue this guy here, and it gives you this surface here. So you can construct this Segal amplitude in this setup. Okay. Questions? Yes.
What's Hilbert space like?
So, so the good question, yes. But I will. Yes. I forgot to mention. There are two different Hilbert spaces. There is one Hilbert space that will attach to each bulk cut, and one different Hilbert space that will attach to this boundary to boundary cuts. Okay. So there are two different Hilbert spaces. They are both Fock space, but the Hamiltonian and the structure is a bit different. You have basically in the bulk cuts you will have your two copies of the Virasoro-Algebra. Here your Hilbert space for the boundary to boundary will carry only one copy of the Virasoro-Algebra. Okay, so one nice aspect is that the theory with boundary is way more rich than the bulk. So, for instance, there are many possible structure constants. Of course, you have always a structure constants, the Riemann sphere with 3 points, the DOS. But in addition, you have everything that can come from the boundary, cuts. So you have one kind of degenerate guy here that is you have a disk with a marked point. The field can fluctuate on the green boundary, and you have a marked point in the center. This is called the FZZ right? Maybe you have this case here where you have still the marked point in the center and 1 point on the boundary. You have this one here with 3 points on the boundary and this 2-point function here, that should be more thought as a reflection coefficient in that case for the boundary. But these two guys here, these two guys are the main ones. They are not non-degenerate in some sense, because if you double them, the double means that you take the Riemann surface, you double it, take the same copy and glue them together. If you double them, here you have a Riemann sphere with 3 points. Okay, so this coefficient here and here, you can think of them as half those, just geometrically, okay? So it will be related to the fact that when you cut the surfaces with boundary, you may have half points. Okay, so these two guys are the most common ones. This guy is kind of degenerate version, the reflection coefficient for the theory, and this one is a degenerate guy. All of them were computed by a series of works. Each of these structure constants takes some work to be proven, and so the nice part in this story, I think, is that initially there was some probabilistic arguments coming from the Uville CFT stuff, say. But then for some of them, I don't remember exactly which, but I guess this one in full generality and this one as well, right? It required a combination with the couplings of GF. So nice probabilistic couplings with the SLE type curve. So this was proven by Jean and collaborators in the past few years. So everything is computed. That's the message. Okay. So now so now you have still semi-groups of annuli, but there are of two types. There are always this old bulk semi-group of annuli. So this annuli, but for the cuts coming from the boundary, you have a new type of semi-group that is formed by this half annuli. So again, if you double this guy along the green curve, you get an annuli. So that's why we call it a half annuli. And so this guy forms a semi-group, and you can implement more or less the same strategy as we did before, but the Hamiltonian is different. Furthermore, he has several parameters, because here you have a value for the cosmological constant on these two parts of the boundary. So the Hamiltonian is way more complicated than the bulk if you want to perform the analysis. And actually, we are stuck. So we can perform the spectral decomposition, but we are stuck with some value of gamma that is not the full range of possible gamma. We are stuck with gamma squared less than 2. We can remove this condition, but under some constraint on the muse. So here it's way more technical. We don't have a complete picture. But anyway, you can diagonalize this guy. You get a family of eigenstates. Again, they are indexed by Young diagram, but now you have only one family of Young diagram. This means that actually this underlies the fact that you have only one copy of the Virasoro acting on the primary state. Yes.
What's the eigenvalue? Yes, it depends on mu b 1 and 2.
Yeah, the eigenvalues. The eigenvalues. It's always q squared plus p squared divided.
Depend on the muse.
They don't depend on the eigenvalues don't depend on the muse, but the eigenstates do.
So your mark point at the boundary when the mu changes doesn't have an anomalous dimension.
The scaling exponents are the one you know, so the quadratic relation always in the alpha.
And that should appear here, no? The spectrum of your Hamiltonian. That's the smallest eigenvalue should be the scaling dimension.
Yeah, but no, but the P is in R plus. I mean, I have no statement on the eigenvalues here, except that you can read it from here and that guy here.
They don't depend on mu.
The eigenvalues, they don't depend on mu.
Higher than 0.
For mu, larger than 0 is. But maybe there are complications. Yes, when that's what you're thinking of. There are some complications about the spectrum may be dramatically different when you analytically continue the operator in the muse, but that's far from what we consider here. The muse are real in our case. Do you have something in mind, like a paper by Teschner or something like that?
Not really, but it's just that the spectrum of these guys with the state operator correspondence will give you the scaling dimension of the boundary changing operator. That's why it should depend on you, I think.
Perhaps, but
your operator depends on the mu itself.
the operator, the age.
Yeah, the age.
The age depends on the music, yes. There are boundary potentials. The operator depends, the eigenstates depend, but not the eigenvalues. Further questions?
Maybe there is a funny thing to notice. So not on the spectrum, but if you take elements on the catch table, so depending on the value of this muse, so you can have some various modules which may be irreducible or not. So if you take generic values of this parameter muse, you may have some non-irreducible zero modules. But if you take them to satisfy some condition, like the one that you take to get these BPZ equations, then you have irreducibility of these zero modules. So this is also a different way, like how these parameters influence the structure of your theory.
But do you understand the structure of these modules?
On the spectrum line, that's clear. There are the
Spaces or
irreducible. On the spectrum line means they are irreducible. Of course, there is the same story that you can continue in alpha. You take this guy as being alpha, you can continue it, and then you have a very weird Virasoro modules. But he said that may be super complicated. And even more, because here we are stuck with probabilistic representation. So I said you can continue them in alpha, for sure, but with the muse here that are real value, positive. But then it's there are some papers in physics where the picture is even more complicated when the muse can be turned to anything. And even the spectrum may be fancy.
but they're still highest weight or the logarithm?
They are all highest weight. Here in our setup, they are all highest weight.
All highest weight. So there's no logarithm.
No, not here. If I have time, I have another example where I have indecomposable but not irreducible stuff in the spectrum. Okay, I won't discuss so much, but the outcome of this story is that if you implement the correlation function, so you want to compute this guy, the S means here that you are on the boundary, just different notation, breakpoints, boundary points. So the S are here, the X are here. You have the same type of bootstrap formula, of course, under this condition here. You have the same type of bootstrap formula, except that now you don't have the modulus squared, you only have the conformal blocks. Okay, and the conformal blocks are those of the Schottky level. So, for instance, if you if you want to compute this this correlation function associated to this surface mark points, you double it along the green curves. You get the double, that is the closed Riemann surface, and you take the conformal blocks on this one and you plug it in this formula. Questions?
What do you do with this formula if your boundary circles are not geodesics?
Here, boundary components that are not geodesic.
Right, so if you do the Schottky double, you still have to pick some sort of metric, which
here for the metric, you don't care so much here about that because the Schottky double.
So that's just the blocks I see. Then you get a different metric factor, which
The complex as a Riemann surface. No, you don't care about the metric.
And
You can always reflect Riemann surface with boundary.
But you need a metric to define the amplitude.
Amplitude, yes.
no, but here you don't compute here this guy you don't compute the amplitude. You compute the conformal block.
The left-hand side is an amplitude.
The left is an amplitude. This one is just a Riemann surface.
Yes, there is a constant, maybe metric
And
constant.
there is this constant here, but these guys, this correlation function, they only depend on the metric through. You can always change the metric here, and if it will give you a global factor. So you can pick the metric, the most nice metric on Earth, the nicest metric on Earth, and then put it here. And it doesn't change anything because of the value invariance. Once you know for this nice metric, you know for all of them. Okay. Yes. So another example. So I would have needed perhaps more time than what I need, but let me just explain. The message for the last part of my talk will be that you can construct another nice example in probability. I won't discuss the physics motivation. It's too complicated. We had several talks about that this week, but I will just explain what, as a mathematician, you can be interested in. So this is a path integral. So what you want to do here is to perform just the change of parameters so that the gamma we had played before with becomes imaginary. So you want to perform this path integral with just change gamma to I gamma, and you will end up with this action here. The point is that there are many options to make sense of this action functional, and the one we choose here is to integrate over maps that are defined on the surface, but taking values in the circle. It will compactify a little bit the problem as if you're on the real line. You can want to compute the spectrum of the Laplacian. You can also compactify by looking instead of function defined on the circle, periodic function, and then the spectrum of the Laplacian will compactify a bit. Okay. Yeah, there are possible extensions where you may want to integrate here over the real line. The function defined taking values on the real line, but it's way more complicated. Here it's a setup where you can try to do something and look what kind of CFT you have in the end. Okay, in the end, so I don't know if I have time. When do we stop exactly? I will cable because we started a bit late, but I don't know if you want to stop at this original time.
10 minutes, 5 minutes.
Okay, let's try. Okay, so there are correlation functions that are given by electromagnetic operators. So what is fancy with these correlation functions compared to what we had before is that the fields are not scalar anymore. Means that you have not R here. So they will carry a spin. And this CFT, well, define the CFT. If time permits, I will explain a little bit. Define the CFT, but it's a log CFT. Okay, we don't know how to solve it yet. There are Yang here and Yu Shao there trying to solve this problem. And this part of the story, this is something we have done with Antti and Paulin. Okay, let me explain a little bit this construction. Okay, so you want to perform the path integral, and I skipped all the slides corresponding to more complicated surfaces because the construction actually turns out to be difficult at some point where it's completely unexpected from scratch. Okay, the problem in this story will be to define the linear term in the probabilistic formulation. You may say, well, if I want to integrate a function on a surface, that shouldn't be too hard, but I'm not drunk. The thing is that here, this is a story about fields that are multi-value. Okay? And the phi here is not a fairly defined function. It's in the story, what you have to extract from the 10 minutes I will talk about this guy is that you are integrating over multi-valued function. And so defining the integral for multi-valued function here, this term, just this term here, take any univalued function, even if it's not random, take it multi-valued. If you want to integrate it over a surface, it's complicated. You have to tell me how you do this. Okay, so there are lots of regularization in this linear term, and I will skip this explanation today. I just want to get to another point that you have a lot CFT in the end, and to tell you just a little bit about that. So I won't explain this term, but the potential here is called the imaginary chaos. So it's just the same philosophy as before, but instead of having a parameter gamma that is real here, you take it complex. The phase diagram for this model is a bit different, but you can still do it with probabilistic techniques, and it gives you a constraint on the parameter that beta squared is small enough. So the central charge in that case is less than -2. There should be a way to define the model for beta squared between 2 and 4. In that case, you reaches the values of the central charge between -2 and 1. Okay, but the probabilistic construction is more complicated. One other constraint, but perhaps I'm not sure to which extent we can. Perhaps there are extensions. I'm not sure, completely sure about that. Is that function on the taking values on the circle, more or less, it's a story of periodic functions. Okay? So if you just look at the zero mode of the theory, you have a Q here and you have a beta here. And if you want to make a sense of this guy, to be well defined as with an input that is a function of the circle, it gives you a constraint on the periodic part of this multi-valued function, and you have another one coming from here. And if you combine both of them, they tell you that the central charge has to be rational. Okay, so perhaps there is a way to go beyond this constraint. I'm not completely sure, but the obvious. If you want to start in the most simple situation, you have to impose that beta square is rational for periodicity conditions, issues actually. If you combine both of them, you get that beta square is rational. Well, so there is one thing still. This is when you define this guy here as this limit, you want to plug it here. You have another problem is that you have to take the exponential of this potential and show that it has exponential moments, so that the expectation of this exponential of random variable makes sense. This is something you can do with probability. And so you more or less end up with a well-defined model. But I didn't tell you how to construct the correlation functions. And that's what I want to do in a few slides. So the first and the most simple operators are these electric operators. This is just exponential of the field, but now the parameter is imaginary. In the sense, this guy is real, and you have an I in front. And the charges here have to be quantized in a way that they live on the lattice. Well, on the Riemann sphere, you don't have this constraint, but in more general situation, you have to impose this condition. Okay, so these are the first family of correlation function that you may want to plug, and actually you can make sense easily of this this setup. For this, you just have to implement. In physics, it's called complete the square trick. In probability, it's a Gersonov transform, and I think the physics terminology is very efficient in describing what it is. It's just a simple change of variable in the probabilistic expression. And so to define this correlation function, this is more or less the same construction as before, but now the field phi j is you have a constant mode living on the circle, a GFF, and you further plug a deterministic shift, which is just this is the green function. Okay, so this Gaussian transform, it takes the GFF that you have in the beginning and you shift it by this deterministic function. It gives you a well-defined expression for the correlation functions. And these are the operators. But now there are a second category of operators called electric. So basically, if you have a configuration of points in the plane, you have your surface. I am on the Riemann sphere. Okay, so you want to force your field to have some windings around some points. So you're on the Riemann sphere, so the blackboard, and you have some weights here, M1, M2, integer weights, M3, M4. What you want to impose to your field, phi, is that when you make a turn around this point, okay, your field shifts from 5 to 5 plus 2 pi M1 R. Okay. So when you make a turn around this point, because it's a multivariate function, when you make a turn, there is a monodromy for your field. Okay, and you want to force the monodromy around one given point to be this weight M1. Okay, so how you do this? How you perform the construction? So if the sum of the weights is 0, you can find a holomorphic one form that has the prescribed windings. Okay, and then you shift your field by this integral of the one form along a path that goes from x0 to x. Okay, the problem here, okay, this is the source of the problem. The problem here is that this integral along the path, of course, it depends on the path. Okay, because for instance, if you start from here, x0, you want to go here. There are 10,000 ways to go from here to here. This one, but you can also make this one. But if the difference between these two paths is the winding here. Okay, so you have to show that all the quantities here are well defined, whatever the choice of the path here. So you have to have an object in the end for the correlation function here. This object, you don't want to depend on the chosen path. Okay? So there is a strategy to do this. It's based on introducing branch cuts. Okay, if you are given a branch cut on the plane, there is a branch cut is something a graph in the plane outside for which the complement is simply connected and perhaps not simply connected, but connected by arcs, and where this guy is exact. Okay, so you can define the integral. But of course, then the path integral depends on the choice of your branch cuts. And that's a huge problem because this means that this guy is not well defined. And then this is why you have to play with this guy here, the curvature. If you regularize it in some way, you can prove that the path integral here that you have defined does not depend on the choice of the branch cut. Okay, but for this, it's not enough to have just the location of the points. You have to prescribe at the z's some unit tangent vectors that will determine in some way the branch cuts. And this is why you have spins. Okay, so the correct formulation for the magnetic operators is to add at the z some unit vectors. So here you have a z. You have to prescribe some unit vectors at each point. So here, here, and here. And there will be a strategy associated to the choice of branch cut. Then you regularize the curvature, and then you show that the path integral is well defined and does not depend on your choice. Okay, and in the end, what you want to do is to have the more general possible correlation functions. So you merge together the electric operators that are defined at different mark points. You have magnetic operators defined at other mark points, and then you force the points to collide, electric and magnetic, to form a more general family of electromagnetic operators. They carry an electric charge and a magnetic charge. And they are defined under some conditions. Okay. The point is that they have the usual deformation invariance, local scale covariance. The weights are given by some expression. The central charge I told you about. There is a spin, meaning that if you rotate the vectors, you get a phase in the correlation functions. It's a bit quick as a story, but there are well-defined correlation functions for the model. And furthermore, one interesting thing is that if you look at the three future constants, they are given by a square root of the imaginary dose. It means that if you normalize by the spin and the diffo invariance, the value invariance, you can reduce the structure constants to 0, 1, and infinity, but then you can also fix the orientation of the unit vector. And on the plane, I fix it to the canonical one or whatever. And then you end up with a formula that is the square of the imaginary dose, the square with a twist. Here you have the conformal weights of the three guys and their conjugate. Okay, so it's in some way it's a square root of dot. That's a fancy structure that was already observed in physics in some cases. Okay, you can. Well, I will try to finish in one side. So you can perform the Segal axiom. You can also identify the Hamiltonian with the same story as before. You get an operator H. But this time, this operator is not self-adjoint. I wouldn't describe it so much. Yes. So you have an operator. It has the same flavor as we've seen in my lectures, except that now the guy here, the potential is an imaginary GMT, so it's not real because you have an I here. So it's not a real potential. It's a complex one. And so it's not, the operator is not self-adjoint. Okay, but still we can completely compute the spectrum. Does not depend on the spectrum here means eigenvalues. The eigenvalues, even so the potential depends on me, the eigenvalues don't. And so the thing is that we know that this H it can be decomposed into Jordan blocks. So it should be a log CFT. But one thing is that these blocks they may be arbitrarily large. Okay, so that's a bit complicated, and that's something Yang and Yusha are looking at now. Okay, so I'm done. Yes.
The pure magnetic operators, they have spin or not?
Pure magnetic. If you take pure magnetic, the spin is here, you take alpha equals 0. So it's just given by the Q.
So if Q equals 0, they don't. But
if Q equals 0, they don't have. That's what you expect. But the Q produces something else. And actually, this Q here.
We need Q non-zero. We cannot do Q equals 0.
Yes, I mean, you can.
if you just do a compact GFF,
You can at beta equal 2. But this is what he is talking about.
just compact GFF, which is nothing.
We don't know how to define.
No, but what he has in mind is the Q, because he's used to the C equal 1 theory. And so he wants the Q equal 0, but this is corresponding actually to beta equal to 1. Yes.
So what made the compactified theory easier than the full imaginary rule?
Easier?
Like why can we construct the compactified version but not the full version?
Yeah, so actually no one is simple. The difficulty the difficulty is somewhere else in both cases. Here the difficulty is in the bootstrap because you have a non-diagonal theory, log CF, log stuff and so on. So here what is difficult here No. Here, so here, when your function take values in the circle, the zero mode means that it lives on the circle. Okay, so basically, if you just look at the zero mode, the integration measure here is a compact. So that's nice enough. For the imaginary Liouville, the functions here take value in the real line. The zero mode is free to fluctuate, whatever it is. But then if you want to make sense of this quantity here, you have this potential here. Basically, you're looking at the expectation of this exponential of this guy. You have to tell me the behavior in mu of this random variable or of this Laplace transform. Okay, you're looking at this quantity here. As a function of mu. And the behavior of this guy is just crazy. Okay, there are super fancy situations that we are looking at with Romain, Raoul, Colin, to define the path integral. So you have to look at the behavior of this guy. I can try to draw something. If you look at this, so but you want to know the whole difficulty is to understand the behavior of this Laplace transform when mu is a complex parameter. Okay. If I don't mess up the orientation of my board, it decays when mu is. So this is the mu phase here. It decays along region actually like this. There are pelvic region where shifted half strip in this direction, where the field decay, this guy decay in this direction. So then you want to integrate the zero mode in, and there is a singularity in between. So you want to integrate the zero mode, not on the real line or something like that. You want to integrate these guys along contours that come from it, plus infinity in some way, and come back by another. But proving this mathematically, it's a real mess. And even numerically, it's not always easy to understand what happens.
You said decay, but numerically it looks like it's decay.
Sorry?
When you say decay, numerically it looks like it's decay.
Yeah.
Because proving is.
But I believe my laptop. So it decays, yes. But it's not proven, of course. And so when you do this, you have a very defined path integral. We have checked with Raoul that the structure constant, it's really the imaginary dose numerically. But then you have to understand the spectrum from this weird path integral and so on. That's a mess. No more questions?
So if there are no more questions, let's thank
by the way, I forgot to mention that we will organize with Evelina Peltola, Cher Jean Mollet at the CIRM next year. There will be a summer school in August at the CIRM. The topics are those of the programs similar. So for all the people who are students and for all the students that are interested in, you can go to the site of the Cher Jean Morlet. I don't have the link, but you Google Jean Morlet, the Cher. So it's in the CIRM in Marseille, and because we are good organizers, we managed to get the CIRM and the school in August in Marseille, so it's close to the Calanque. Don't hesitate to come. It's a nice place, and that will be a nice school. Thank you.
So I think we start. Let's say at what is it now? You see at 35, we ring the bell.
好像是一个冠名的活动，他们也都有。